Welcome back to system software. So we're pretty much in the middle of our compiler half of the class. We went over everything we need for CodeGen 1, so hopefully everybody's getting started on that. Let's see how much time there's left. A week left for CodeGen 1. We went over arithmetic and branching, and now we're going to go over what you need for CodeGen 2. The CodeGen 2 project is released. Just as a note, these are separate projects, so you'll re-download the template and upload to a separate repository. If you put all these projects together, you can make a complete compiler. I encourage you to try that. It's fun to see everything work together. But they're separated out just so, because these the compiler projects are sort of dependent on each other. Like if you mess up one, the other project is not gradable. So it's separated out for you into 3 separate projects. So just repeat the process. It's a new URL. It'll be CodeGen 2 instead of CodeGen 1 for the Git URL, which is somewhere here. It'll be CodeGen 2 instead. So just be aware of that. Don't try to submit this in CodeGen 1 because we won't grade it with the CodeGen 2 test cases. All right, questions on anything from last time, arithmetic, branching, questions on the project? Who started the project? Okay, a bunch of people. All right, that's good. Any questions on that? So the code will actually be pretty small, deceptively small. It's just the idea behind it and testing, it's going to be tricky. Yeah?
Are we going to wait forming it to simple IR?
Sorry, say again? Speak a little louder.
So when coming to working on those functions, the ones that we have to implement by ourselves,
Yeah.
are we trying to word it in a way for simple IR or assembly or both?
I'm not sure what you mean. So simple IR is the input, and then you generate assembly. Yeah, simple IR is the input, and then you generate assembly code. So the parser will handle all of the processing of that simple IR, and it'll give it to you in a yeah. No, you don't have to do that. You don't have to do that. So you just follow so if you read go to the manual here, or the handbook, I call it, and it'll walk you through how to use the parser framework, how to get access to the input, information in the input. So here, if you've got a arithmetic operation like this, and the parser will turn that into a tree for you, and if you want to access the parts of that statement to get the destination variable here, which is here x, you use this field to get it. So this field, this is just think of these like structs. They're objects in C++, but they have the same syntax as structs. To get this left operand y, you use this object, this field. To get the operator, you use this field, and to get the right operand, you use this field. Does that kind of make sense? So that will be available for you in the, so there'll be this CTX variable that's declared. This is enter call. This is not enter operation, but enter operation will have a similar function prototype. So the way this works is the parser framework will do the tree walking for you automatically. If you remember, we talked about using tree walking to implement languages. It'll walk the tree, and then whenever it sees a node in that tree of this type, whenever it sees a construct, it will call this function for you. And all you have to do is write the code that runs whenever the parser sees this kind of node in the tree. So this is called the visitor pattern, if you learned about design patterns. So yeah, all you have to do is fill in the code for each of these functions. And so what the code will do, the code just needs to spit out assembly code, equivalent assembly code. And so the handbook here will show you what variables you need or what fields you need to access in order to get each piece of the input language. And this here is an example of translating this statement into equivalent assembly code. And there's descriptions here as well about how to write the code. So this will tell you how to translate the operands into assembly operands. This will tell you how to test the operators. So the operators will be it'll be in a tree, it'll be a symbol in a tree, and these are the names of the symbols. So you just compare these with the operator type. Just compare that to see which operator was input by the user. Other questions on this? So yeah, as I said, the code is like deceptively short, but the concept, this compiler concept, is the tricky part because you're spitting out assembly. Yeah.
More complicated process.
What's that?
Like a more.
Yeah, exactly. Yeah, it is. So it's like a more complicated process project. Exactly. So in the process project, you wrote your own parser, which turned the input language into this in-memory data structure, and then you gave it meaning. You named all the structures like command, or I guess I gave you a data structure for it, but you named all the structures like command, pipe, and then you wrote an interpreter that went over that data structure to interpret it, to run the program. Here, we're doing something similar, except, yeah, it's a more complicated language. So we have all of the syntax parsing done for you, the syntax tree given to you, and then instead of interpreting, you compile, which means you just generate code in a new language. But yeah, the shell project, the proc project, is like a small version of this. Bless you. All right, other questions on the CodeGen project? So start it if you haven't. It is a little, you just have to wrap your mind around this idea of a compiler. And then, as I said, CodeGen 2 is now out. CodeGen 2. So yeah, it's good to do CodeGen 1 first, because CodeGen 2 we're going to be compiling pointer operations. And this is going to get confusing really fast, because your compiler is not performing any pointer operations. It's generating assembly code that should do the same thing as the input program. And I'll show lots of examples and show lots of diagrams to show you this. But if you don't understand pointers quite yet, hopefully you'll learn them here, and you'll learn them, and even if you know them, you'll understand like why and how they work the way they do. So yeah, this is the project. These are the functions you have to implement. We won't test any of the arithmetic or branching stuff in these tests. It'll just test these three parser functions, or these three visitor functions, corresponding to the three pointer operations in our language. All right, other questions on CodeGen, stuff from last time, compilers in general, assembly, simple IR? All right, let's go over the homework. Okay, this one, it seems like an extensive extra homework. I hope people didn't spend too much time on it, but I just wanted you to basically do the branching behavior in this one. If you did a full translation, great. That'll help you. That'll help you for testing the project. Or you could use your CodeGen 1 to actually translate part of this. But I really just wanted to have you practice the branching behavior in this program. So questions on this homework first? Any questions on it? Okay, let me. Okay, so the first thing that you could just use the symbol table that we had in our class. So if you got this wrong or didn't think about it or were confused about it, don't worry about it too much. In the compiler project, this is just given to you. The code is given to you to generate the symbol table, but I'll just make one here. So A, B, I think we start at negative 16 in class, but don't worry about this. This will be given to you in the compiler template. Oops. Oh, did some computation for me. Any questions about the symbol table or differences or concerns? Look good on the symbol table? So it didn't really matter what you had for the symbol table because, yeah, as I said, the code I gave you will do that for you. Okay, so let's start with the first branching related code. So head, the head label. How do we translate that into an assembly language label called head or called anything? Yeah, it's like identical syntax in assembly. So in the assembly language, it has basically the same syntax as simple IR. Questions about that? So that enter label visitor will be hopefully very, very easy to write for the pointer class. Okay, All right, what about this if go to? How did we translate, or what operations did we use, at least in our translation? Remember, there are many ways to translate the same code. How did we translate it?
Remove whatever A is into REX.
Okay, so we need to, get the first operand into RAX, or any register really, then.
Compare it to 0.
And then, compare it to 0. So in the pattern I gave you guys, which I think makes compiling easy, I will get the second operand into RBX, and then compare RAX and RBX, and then what?
And then you would use the jump less than.
Yeah, so we'll use jump less than or equal to whatever our label is, which is here A1. I think it's A1, yeah. Questions on the pseudocode of the translation? So that was like the template we had from class. All right, so getting the first operand. Anyone remember how we can get, so the first operand is A, the second operand is 0. So how do we get the first operand? How do we translate this access of the A variable into assembly language, access to a memory address? Yeah.
Would it be like 5 RAX,
5
comma RAX?
RAX 5. Where's 5 come from?
By,
Oh, because A is 5. So technically that's true, actually. So if you had written this, if you had said, and in the AT&T syntax should be, you could have done this, and that would be a correct translation, actually. Even though it's not like a literal translation, that would be correct. Because as long as the program is equivalent in all inputs to the program, all inputs are the same, have the same outputs, that technically is an equivalent input. Yeah.
Another way to do it is you could just do the offset and then do it by, which would be like -8
And what is it?
RB.
RBP, yeah, into RAX. Yeah, that's right. So both of these are okay. The first one, this technique of taking variables that are constant and substituting them where the variable is, this is called constant propagation. And it's a technique that like all modern compilers do. And it's for efficiency because this operation is much faster than this operation. It's much faster to do an immediate load than it is to do a memory load. Yeah.
Well, when you're able to reassign what the variable is, it's still called constant? Or if it's when it's declared outside of the...
So this is where things get really, really subtle because, actually in this case, you have a good point here. So depending on how we translated the rest of this code, A is being changed here. So actually this would not, depending on what we do next, depending on how we translate this may not be equivalent. So if we had done this and then put go to head here after we do all of the, A minus A equals 1. So if we always compared 5 to 0, would this be an equivalent? Like, can we just substitute A for 5 here? Would that be correct? No, right? Because A is changing. Now there are other compiler optimizations, for instance, loop unrolling, that can detect that not only is this a constant, but that this loop will only run 5 times, and just copy the loop 5 times instead of actually having the branch. So another possibility to do that. Now, trying to work out all these optimizations while translating with your compiler is a massive pain to do that. So like I was talking about last time with the redundant go-tos, the easy way to do this is to just translate in the most formulaic way first. That makes it easy to get things right, and then use later algorithms to optimize the compiler. So to make it easier here, I'm going to avoid hard coding 5 here, avoid doing the constant propagation, because then I'm going to have to do loop unrolling to make this actually correct, make this equivalent. So let's just do the formulaic way of translating this. So if you're interested in compiler optimization, you can read about it online. You can take compiler construction here, or I don't have it. I don't know if I have anything online, but you can find online materials seeing how this stuff works. But okay, so let's just always load it from memory. That way we don't have to try to figure out when it changes or when it doesn't change. So if we always read from memory, it will always be equivalent to the simple IR program. Okay, so that's the first operand. What about the second operand? Second operand is just 0. It's always 0. So we can move it into our BX. And then to compare, we use compare, and what are the arguments to the compare op?
RBX, RA.
Good, RBX, comma RX. Why not RAX, comma RBX?
Because they're considered
Yeah,
the
the
RX is the one being compared, not the first one is what's comparing, the second one is what's being compared to.
yeah, exactly. So just the quirk of the AT&T syntax, the destination operand is last, and because comparison is basically a subtract operation, to be consistent with that, the second argument is the left operand of the comparison. Okay, and then so that's the comparison. Questions on the compare operation? This will set the flag register in the x86 architecture, which will keep track of whether the result was 0 or 1, or sorry, 0 or non-zero, less than or greater than. And then we can use one of the branch operations with a condition code, in this case condition code LE, to conditionally jump to A1. So A1 is somewhere down here. All right, questions on this translation? So then there's going to be some code here, which I'm not going to translate because it's part of the arithmetic lecture. And then translating goto is, so yeah, how do we translate goto? Jump. Jump is the unconditional goto. So here we have the translation of the branching behavior of this code. Questions on this translation? So another kind of optimization question. Do we always need to move 0 into RBX here in this code? Maybe, maybe not. Depends on whether we use RBX down here. So if we had set RBX to something here, then RBX is going to change. It won't be 0 anymore. But if we're really clever, we could either keep 0 in RBX, or we could propagate 0 here, so it's always comparing to 0. So again, more optimization opportunities. But just remember, don't do that while translating. Do the formulaic translation first. Follow the rote way to do it. That's easy to convince yourself that it's correct. And then there are all sorts of fancy techniques for doing automated optimizations that are correct. Compiler construction is the place where we learn about that. All right, okay, so I think this is all the branching behavior. Questions on any of this? So if you got something different, it doesn't necessarily mean it's wrong. It just might be use different registers. There's lots and lots of ways to write code to have the same inputs and outputs. Lots of equivalent programs. Actually, an infinite number of them, technically. Infinite number of equivalent programs. All right, any other questions on homework? Branching, arithmetic? Okay, let's do attendance. All right, so let's get into pointers. And so it's not a huge amount of material, but I'm gonna try to take it pretty slow, and it's over 2 lectures, so we got plenty of time to go over pointers. So the first thing is we're gonna just kind of do a little refresh of pointer operations, because I know this is like a confusing part of C, and simple IR works basically the same way. So we've got 3 pointer related operations in simple IR. The first one is reference. Has anyone seen reference before? Ampersand? A little bit, okay. Has anyone never seen it? Okay, so hopefully everyone's seen this. So it's just ampersand X, and it takes the address of X. Now, that's just kind of a confusing way to say it, because what does it mean for a variable to have an address? It doesn't really make sense unless you understand what the compiler is doing. The compiler is translating, when we learned about the symbol table, the compiler is translating variables into memory accesses. So in the C language, there's no real notion of an address. There's just symbols. But now that we saw a little under the hood, these variables are stored in memory addresses, so this reference is taking that address where it's being stored in the machine. So not the value of it, that's what's in the memory, that's what's stored at the memory address. Okay, so reference. Questions on reference? And then we have dereference. Dereference takes a variable that holds an address as its value, and it accesses the memory at that address. So dereference, just like in C, you use an asterisk to say, don't copy the value of T1, go to that memory address. That's the pointer operation, right? That's the following the pointer to get the address. So we're going to take the value of the memory at T1 and store it into T2. Questions on dereference, the meaning of it? All right, and then we have dereference assignment. In the C world, this is maybe not as clearly delineated, but in simple IR, I wanted to really decompose this into separate operations for you. So dereference assignment is taking whatever the value of T1 is, which is some address, and then storing 11 in that address. So T1's value is not going to be 11. Whatever address T1 has, we're going to go to that memory location and store 11 in that address. Make sense? Questions? Questions on that? Yeah.
The T1 as an integer isn't defined here, right? Just like the
Yeah, that's right. Well, yeah, none of these variables assigned, but yeah, assuming that, well, actually in C, as if anyone who's ever gotten like a seg fault knows, it doesn't even matter if you have a valid address. The compiler in the machine will attempt to dereference that address. So when you get a seg fault, that's because that address is not accessible to you as the user. Or, yeah, it's like an inaccessible address. But the operation, the dereference operation at the machine level is still occurring. That's why you get that seg fault. It's just the hardware is protecting the memory against you, basically. It's protecting the memory locations from you modifying it. But yeah, and we'll see that we'll learn more about types, and we'll see what it means for T1 to have a value or have a valid value or not. But yeah, I'm assuming that T1's the address that T1 is storing is accessible to you as the user. This will store 11 at that address. But yeah, it's good question. This will become more relevant as we look under the hood how pointers are working. Okay, any other questions on dereference assignment, I should say? So we have dereference load or dereference access and dereference assignment. And they're quite different operations under the hood. All right, so let's do a complete example and a little pointer quiz for everyone to see if you can follow along with the pointer. So we've got X assigned to 8, Y assigned to 9, T1 assigned to the address of X, T2 assigned to the dereference of T1, then we have a dereference assignment of T1 to 11, and T3 equals X, etc. So the question is, what value of X gets returned here? And actually, let me review myself. So, okay, we have someone answering. Yeah, what value of X gets returned? Yeah. 11. Okay, who says 11? Who says 8? What about 9? Something else? Good, yeah, it's 11. So hopefully if you got that, then yeah, you understood pointers. Good. So the kind of classic way of diagramming this, the like Intro to C or CS1 way of diagramming this is to do this like diagrammatically. So we'll say something like, all right, X is some kind of box here. It's got 8 in it. And then T1 now gets the address of X as a pointer to X. So we say, all right, well, T1 has like this arrow to X. Now, the x86 architecture doesn't have like literal arrows, but this is kind of a useful diagrammatic way to show what a pointer means, what a pointer looks like. Okay, so this is what happens after we run T1 equals the address of X. Now we have this pointer to X. What happens to T2? So when we say T2 equals the dereference of T1, what value does T2 get here? 8. I heard someone say 8. Why is that? Because we're not taking the value of T1, which is kind of hidden from us. You kind of never really think about what's the value of T1. You just say, well, it's a pointer. We can dereference it. Because we're dereferencing T1, we're following the pointer to whatever X's value was. That's 8, so T2 gets 8. Questions about that operation from the C point of view? Okay, and then we've got this dereference assignment. So how does the state of this machine change when we do a dereference assignment of T1 to X? Does T1's value change? No, right? T1's value doesn't change. Instead, we follow the pointer and then assign whatever memory location that is, whatever's being pointed to 11. So that's where the why do I have 8 in here? Yeah, anyway, that's where the change to X happens. So yeah, so if we had like, yeah, anyway, so that's where the change to X happens. Now X we consider to be this memory location, so we say X is being changed here. Okay? And now we have T3 equals X, and because we're just taking whatever the value of X's memory location is at this point in the program, T3 will equal 11, right? It's not going to equal 8. And so that's why when we return X, we get 11 for X. Questions on this? Questions on this diagrammatic way of showing pointers? Okay, so hopefully pointer review for everyone. It sounds like it is, but let me know if you have any questions. So let's take a look at what it looks like at the machine level, or at least a mental model of the architecture, RAM, registers, and CPU operations. So first, let's recall how we store variables in memory. And again, this is all, you kind of just have to accept this because we're going to learn how the compiler manages this in a couple of weeks. But I assure you, under the hood, at least what like the GCC compiler will do, is it will store all of these local variables in effectively an array in memory. So what our compiler does is it takes all of these variable assignments and gives them an offset from this mysterious RBP register. So, and then, so another way to look at this is we've got this array in memory. How many do we have here? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So another way to look at this is we've got this array in memory. And they're at offsets from RBP. Now, this doesn't really also get us any closer to the actual RAM. So what's really going on here is that there's some address that RBP starts at. So there's some address, and this is really up to like the loader that's gonna do this. It's gonna allocate the space and the stack operations. But again, we'll learn about that more in a couple of weeks. But assume that we know what the value of RBP is. So if we know that RBP, because RBP is minus 16. So if we know that RBP is, say, 120, That's our actual memory address. Then an offset of negative 16 is what? I have to do arithmetic now, which is going to be hard. All right, so we know that the actual address associated with A is 104, right? Makes sense? So if we know that RBP is 120, then an offset of negative 16 from 120 is 104. And we can kind of reverse engineer all of the offsets of, well, no. Okay, so you just go down by 8. So we can reverse engineer all of the actual memory addresses by just subtracting by 8. And let me know if I make a mistake. I will easily make a very simple mistake. What's that? 54, and then 46. Did I get this right? What? 64. Oh, thank you. Of course, I got it wrong. 64 and 56. All right, did I get it right? Basic, like arithmetic. Okay. So this is what the view of what the RAM will look like. This is the mental model of the RAM. That each of these variables is going to get its own slot in memory, or its own space in memory. With me so far on this? So this is the actual address of the variable in memory when we're running this program, like assuming that we know what RBP is. Questions on this? Okay, so let's run this program. So let's rerun this program. So instead of using that kind of diagram, that pointer diagram model, let's look at what actually happens to memory and the state of the machine under the hood when we run this program. All right. So when X gets assigned, as we saw in our lecture on like arithmetic and how variable assignment works, if this is the actual address and this is the contents of memory, then X is going to get 8. So assuming that everything's an integer and it's using the binary 2's complement or whatever representation we use, it's going to have 8. With me so far? Makes sense, right? And then when we assign Y to 9, the memory location associated with Y is going to have the value 9. All right, so what happens when we have this pointer dereference? What does T1's value, or X's value for that matter, how does the state of this machine change when we run this reference operation? What's that? Yeah, T1 gets assigned the address of X. What's the address of X? 88. That's the address of X. So like at the machine level, this is the number that's stored. So remember, all of these are just binary representations. So we get the binary representation of this address, which is also going to be like integer, the kind of classic integer representation. So T1, the memory location is literally going to be 88. It's going to have whatever this address is of this RAM, that's going to be the value. That's what's going to be stored in the memory location. Questions on this? Did you guys learn this? Hopefully you learned this, that it's literally like you may not have learned this. You may have learned the diagrammatic way. So this is why it's considered a pointer, because this 88 is the same as this 88. But to your question, actually, your colleague's question, if I had dereferenced X, what does that mean? I go to address 8, right? So there's nothing intrinsic here, just like this is not intrinsically an integer, or this is not intrinsically a floating point. There's nothing intrinsic about this state of memory making it an address or a floating point. It's the fact that we're going to dereference it later that makes it a pointer. So I think your hand up first. Yeah, what's going on?
I always thought like the addresses, not like garbage values, but they were just like a number that reduced the pointer. Are they always like, are the addresses of pointers always following like the RBP like order?
So the RBP thing, we'll explain this in a couple weeks. This is how a compiler will manage memory. And the compiler and the architecture work together to manage where local variables are stored. But strictly speaking, like this memory location doesn't know anything about RBP. It doesn't care.
Organized, like, from counting down.
Yeah, that's how we organize. That's how we as compiler writers and the architects envision you organizing memory. But you don't have to do it that way. You also have malloc.
Does that have a computer organized?
It's how the compiler does it for local variables. But you also have malloc. So malloc can allocate space in a heap, and again, it'll store a pointer for that. There are global variables. There are other ways to organize memory. But at the end of the day, a pointer just means that variable has a value. That memory location has a value set, but it just happens to be an address. And actually, there's nothing here at this point. There's nothing in the machine that says this is an address versus a number.
It's not the other way around. It has an address that happens to be an integer.
Well, the way these addresses are represented at the machine level are the kind of classic binary representation for integers.
Mm-hmm.
So this will kind of overlap with integers in a sense.
Yeah.
Like they'll be equivalent. But really, what makes it a pointer is that we dereference it. That's what makes it a pointer. So if we dereference this, that would be a pointer, even though we as the programmer didn't intend that. That's why you get seg faults, because you dereference 0, but you didn't mean to do that, or you dereferenced an integer. You didn't intend for that, but the machine doesn't care. All it cares is that you said, I want to follow this memory. I want you to get the value at this memory location. It'll do it. But if you if it's a memory location that you can't access, like low values typically are reserved for the operating system, so you can't access those. So the hardware will protect you against accessing those. If you didn't have the operating system, you wouldn't get that protection. You would just blow away your operating system memory state. All right, so I think you had a question next.
Yeah, why don't we assume it's always going to be, I think, 2 bytes of data?
Yeah, that's a good question. Another question on types. So in our compiler, everything is 64-bit integers. But in like a language like C, the variables, the data types have different bit widths. So integers on a 64-bit machine are 32-bit. Longs are 64-bit. ASCII characters are 8-bit. So the compiler will allocate different amounts of space for each variable. So it won't always be the same. It won't really be like an array, which an array, every element has the same bit width. But in a real compiler, you'll have different data types. They'll be of different sizes. I do it this way because it's just much easier to write the compiler this way, to not have to worry about data types. Everything's the same data type. But yeah, that's a good question. Yeah.
Why wouldn't we store the offset instead of the actual?
That's a good question. Why not the offset? And it's because the architecture isn't really aware of the offset. The architecture can take, so the operations that we use for doing pointer dereference, they just take addresses. They don't do any computation from RBP. They just take like basically absolute virtual memory addresses. They just take the literal address. You could imagine writing an architecture that had a special pointer operations that took into account RBP, but I don't think x86 does that.
So when we're writing out the assembly, we want to use the memory address rather than the offset? When we're trying to...
It's got to be more complicated than that because in order to get this. So I think what you're getting to, or what you're foreshadowing here, is that how are we actually going to figure out what 88 is? So all we have is RBP and the offset, and we're actually going to spit out assembly code that will compute it on the fly while the program is running. That's what we're actually going to end up doing. And I'll show that I'll show that very carefully as we go through all the operations. But that's a good question. We will use the offset to do it, but the machine is not going to do that. We're going to have to spit out assembly code, so the machine will do it for us. Yeah.
So does just for simplicity's sake, do the RBP and the offset equals its memory address? Not always going to be like that. Like the RBP starts out.
To make it.
Incrementing down, yeah. And then
Well, it's just saying, can you avoid an offset and just have absolute addresses? You could. I think that's what you're saying, right?
No. Because you put 104 for the memory address. And
Yeah.
the offset is -16.
Well, it's negative. So I computed this as 120 minus the offset.
Yeah. And that's the memory address, so those are both.
So these are
these an arbitrary offset that if they were to start at 120.
No, these are the offsets. What you'll see is that we as the compiler writers will actually be the ones who control the offsets and what the offsets we use. I'm trying to show an example of when you actually run the program, because it's not up to us as the compiler writer where in memory the variables will be stored, or at least not with local variables to functions. So we won't know ahead of time what location that is, but basically the compiler infrastructure, the system infrastructure will set it up so that once our main program is running, RBP will hold the memory address of the local variables. If that kind of makes sense. It's sort of hard to describe because it involves the other pieces of the system. But basically, for our language, we as compiler writers are not going to know the absolute address that these variables are going to be stored. But we can enforce that they're always an offset from RBP. And we as the compiler writers are making that choice. So this is not like a law of nature. We're going to use that in order to make sure we can keep track of these variables. Yeah. If that sort of makes sense. So you kind of have to like trust me on it a little bit till we see functions, because there's a good reason for designing it like this that we'll see with functions. You could just have global variable allocation. This is like old school programming. So like in Fortran and other languages without modern functions, you would just do like global static memory allocation. You wouldn't need malloc, you wouldn't need functions. You could just say absolute memory addresses. And if you do any embedded computing or like microcontroller computing, you may do this. You might just have a static allocation of memory. But on like larger devices and modern machines, we have heaps and stacks that are managed automatically. So the addresses aren't predictable for the compiler writer, basically. Yeah. Oh, it's a good question. No, this will just be one operand, and then this will be the destination. That's what we'll call it. Yeah. You'll see it in the handbook. It'll tell you how to access each of the parts of the statement. Okay, let me take a look. So enter reference. Oh, I see what you're saying. Oh yeah, it doesn't show it. Send a message on EdStem and I can put that in. But it's going to be very similar to. It'll be like similar to the ones for operations. So it'll be similar to this. It'll just be like operand. It'll be just like enter assigned. Yeah, you can send a message on EdStem and I could add that. Okay, so we've only gotten here in our code, but you can kind of see how subtle this is when you look at it at the kind of architectural mental model of this machine. So yeah, assuming we know the addresses of these variables that we've allocated to store these variables in, when we do a reference, it's just getting this address here. It's getting this address and saving it as the value of that variable. And to the RAM does not know or care what the meaning of any of these values are. It's just going to store whatever bit sequence you've given it. It's going to store it there. All right, questions? Any other questions on this part of the reference? Has anyone seen this? Did they talk about this in like Intro to C or C a little bit? Okay, so you actually get the address. All right, so now let's take a look at a dereference operation. So after the dereference operation, how does the state of this machine change? So we have T2 equals dereference T1. How does the state of this machine change? Any takers? So in our diagram, what happened? T2 got assigned to 8 because we followed the pointer for T1, and at that time it was 8. So how did T2 get assigned to 8 here? Well, we looked at T1 and we took this address, instead of copying this address to T2, the machine interpreted this as a load from address 88. So this instruction here, this T2 equals star T1, this is effectively going to be a load from address 88, whatever address is given in T1. So that's why that's how this state change will occur. So now T2 will be 8. Questions on that? It's dereference load. All right, now we have a dereference assign. So we have T1 dereference assigned to 11. So just like with the dereference load, instead this is like a dereference store. So we take whatever value T1 has, and instead of storing to T1's memory address, we store to this memory address. So we use this address of T1 to find 88, and then we store to that address. We do a store to address 88 and change it to 11. Questions on that? All right, and then finally we've got a regular assignment of x to T3. So that's going to take whatever value is at x and store it into the memory address associated with T3. All right, questions on this? All right, so a little different view. Some of you have seen this, some of you may not have. A different view of what pointers mean. And actually, in my opinion, a kind of simpler view, because you have a much simpler machine where it's just address value. And then you can see pretty literally what actually happens under the hood when you do pointer operations. All right, questions about this? Okay, so now the tricky part. The tricky part is how can we generate code that is gonna do these operations for us? That is the tricky part. Okay, so for assignment, how did we, so we went over assignment a couple lectures ago. How did assignment look in Intel assembly? So let's get our scratch back up. So then we'll remember if we had something like x equals 8 in simple IR, what did the assembly look like for this? And remember how we did this? Yeah, we used move, and then 8, we moved immediate value x, remember destination on the right, and then how did we get the address of x? I think some people were saying it. Yeah, so I think it was, well, okay, so in this example it was negative 32, but yes, it's whatever the offset is, whatever the offset was from RBP. So this is an addressing mode where we can give it this syntax. We can say, here's an address, here's an offset, store this value into that address. That's how we did the initial assignment into 8, into this memory location. So to get a reference, to get the, so if that's how we wrote assembly code to load from that offset from RBP, how can we get the address of x? So how can we do reference of x? How are we going to get that in simple? How are we going to get that in assembly? How does this computation work? So the pseudocode for it is we want to take whatever's in RBP and subtract 16, right? That's what we want to get. So the trick is we need to generate assembly code that is going to do this operation for us. So what assembly code can we write that's going to compute this value for us? Let's say we want to store it into RAX. What assembly program can we write that will perform this operation for us? Add. Yeah, you can use add to do this. And what do we add? What are we adding? So we're adding negative 16.
The starting RBP value?
What's that?
The starting RBP value?
The starting RBP value. So if we just did this to RBP, we'd change RBP, and that would be bad because now our offsets would be wrong. So let's just assume that we've already set up the value in RAX. What value should RAX? The starting value of RBP, right? And we know how to do that. We can take RBP's value and copy it into RAX. And then we can use an addition to add negative 16 to RAX. And this is equivalent to RAX equals RBP minus 16. Kind of makes sense? So we can actually generate code, even though we don't know as a compiler writer what the value of RBP will be at runtime. We can generate assembly code that will result in the address of X being stored in RAX. Remember, the compiler can't do this computation, doesn't know the values, but it can generate assembly code that will guarantee that it'll do the computation for us at runtime. Okay, so that's how we get the reference. Now, how do we store that result? So now T1 is supposed to have that address. How do we store that resulting value back into T1? We saw it up here, right? It's just an assignment to whatever T1 is. So we take RAX, which holds the address of X, and we store it into whatever T1 is. So T1 has offset negative 48. So we're going to store that value, that address of X, into T1's memory location. I'm getting some head nods, which is good. It's good to see. Questions about this? Is kind of making sense? So remember, we're not actually computing this in our compiler. We're generating assembly code that will compute this when the assembly code is run. And since we know, or at least you have to trust me, that this is how memory is stored, memory allocated for local variables, they're all offsets from RBP, we can spit out assembly code that will do this computation for us, that will get the absolute address of this value, and then save that, just like we save any other value to a variable, save it into the memory location associated with T1, just like the user asked us to do. The user asked us to get the address of X and save it into T1. Questions? Questions? Okay. Okay, so I already did the assembly code for this. Oh, was the address 32? Oh, it was 32, sorry. It's supposed to be 32, not 16, but that's okay. All right, so actually, let me update it. So the address of X was supposed to be 32, not 16. So sorry about that. So this should be save. This should be 32 for these. But nothing else changed. It's just I had the wrong offset. Okay, so let's look at what this looks like again at the machine level. What actually happens to this program at the machine level? So I'm going to let me undo some of these changes here. Okay, so to give us a full picture of the state of the machine, we've also got registers here. We've got RAX, we've got RBP, and we don't use any other registers for this. So okay, so let's go over this assembly code. So we move 8 into negative 32 RBP. This is taking whatever the value of RBP is. The value of RBP, we're assuming it's given to us ahead of time before we run this. We'll see how that works in a couple of weeks. But if RBP already has 120 in it, and we do this operation where we move 8 into the address given by RBP minus 32, that's going to load 8 into this memory location into 88. Questions on that? So that's the result, that's the state change that happens when you do move 8 into negative 32 offset from RBP. Okay, what about these operations? So we do move RBP to RAX. How does the state of this machine change when we move RBP into RAX? Does any memory locations get changed? Do any registers get changed? Are you guys still with me on this? So move RBP into RAX. How does the state of this machine change?
So A moves into RAX.
What's that? What?
So the value of RBP will go into RAX.
Yeah, that's exactly it. So RBP will be copied into RAX. Mental model of the CPU, that's all a move does between two registers. Just copies one register's value into another. And what about the state change from this operation? Yeah, so RAX will, after this instruction runs, RAX will change to 88. And then how does the state change of the machine when we do move RAX into negative 48 offset from RBP?
So we put the 88 into the negative 48.
Yeah, it's going to take whatever the value of RAX is, and the address to store it at is given by this operand. It's going to be whatever RBP is, minus 48, which is here, which is the address here, and it's going to store that value into memory at that address. Now you can see, without knowing anything about the variable names, or without knowing that RBP, these are offsets from RBP, so all this information here, this is like the compiler information. The compiler knows there's a compile time, but this is what the machine knows at runtime. The machine doesn't even need any of this information. It just needs this information, the RAM and registers, and because of the way we generated instructions corresponding to this, we'll get the right behavior, the behavior we expected. The address of X is now stored into T1, just like the user asked us for, by doing a reference operation. Questions on this? I can't tell if you're very silent because it totally makes sense, or because it's boring, or because it's not making sense. But you kind of see how that works? So we've taken this sort of high-level concept of pointers with diagrams, and we've shown, by translating it to assembly, how operationally in a machine that just has RAM and registers will actually affect the same behavior as this kind of abstract notion of pointers. So you don't necessarily have to do this in order to understand pointers, but I think for me at least, it helps understanding literally that just the integer value of the address is being stored in RAM. And this 88 doesn't have any meaning to the machine. It only has meaning because later on, probably in next lecture, we're going to write operations that will copy out this address and use it for a load or store operation. Questions on this? Yeah.
So if it's an integer value, why is there no dollar sign on the add?
Oh, sorry. Yeah, there should be one. Thank you. Yeah, there should be one for GCC syntax. AT&T syntax. All right, other questions? Thank you for the catch. Other questions on this? Does this help understand pointers a little bit, maybe? So and this is true of all the machine operations. This RAM is just giving you 64-bit slots to write binary data in. The machine does not care what data type that you as the programmer think they are. The compiler is what's making sure that they operate the way you expect. All right, let's see. So I think I went over this already. Yeah, so you just start with RBP, do the subtraction, and then store the result in T1. This is the exact same code that we looked at. And fortunately, this was right. It has that. All right, let's preview dereferencing a pointer, and then we'll go into detail about this next time. But this operation where you put parentheses around an operand, this is called a register indirect move. It's the same thing we saw with RBP. So this is like the star of the assembly, of the Intel assembly world. Without these, let's see if I have this in here. So without these parentheses, this is just moving the value of RAX into RBX. With these parentheses, this is actually a load from memory. So this, in the Intel world, this means get the value of RAX and look it up in memory. So this operation here, this is a dereference of T1. So this is saying go to RAX, get this address, and do a load at that address instead of actually copying this value. This is what can be a little confusing about the Intel worlds, because this move mnemonic actually represents I think dozens of different operations, and one of them is this register indirect move. So this is not a register copy like in MIPS. I think MIPS probably separates register copy and load and store, right? But in the Intel world, move is like the universal data movement opcode, or operation mnemonic, I should say, and then it gets assembled into different opcodes. So in this case, this is gonna take this location, this address, and use that to do our store into memory. All right, I think I can go over this. All right, so to do our deref instruction, so this is the instruction we want to compile here. So our simple IR. This is the simple IR we want. So in assembly, the way this works is we want the value of T1. We want to get the value of T1, the variable being dereferenced. And then we want to do a load from that address, whatever address we just loaded for T1. And then store that into the destination variable. So I'll just go over the assembly code real quick, and we'll do it more in detail next time. So here's the loading of the value of T1. This is loading the value of the memory address that T1 had. And then this is storing that value into T2. All right, so there's only 2 minutes left. I think your brains are already a little stressed from the, stretched out from looking at this pointer stuff. So let's leave this for next time, and we'll go into more detail. Let me know if you have any other questions or you missed attendance. Otherwise, have a good weekend, and talk to you next time.